I think we can start.
Yeah, I think so too. Yeah. It's 5 minutes past 3, so I would say we could start. So hello everyone. My name is Cătălin Constantinescu, and together with my colleague Nicus Creșeranu, we are hosting this webinar, the third webinar in RIANA, and the first in 2026. And today we have a speaker, Dr. Alexei Maximenko, a researcher from the National Synchrotron Radiation Center, Solaris, from the Jagiellonian University in Kraków in Poland. So Alexei will present to us some information on X-ray and synchrotron X-ray analysis. Please, Alexei.
Yes,
you can start whenever you want.
Thank you, Cătălin. Thank you, Nico, for giving the opportunity to present you the, let's say, basics and the insights how the synchrotron X-ray absorption spectroscopy could help us, I mean us researchers, how we could probe the matter. Once again, I'm Alexei Maximenko from Solaris in Kraków, Poland. And before we start, I would like to announce that if you have any questions during the presentation, just write them in the chat. Then Cătălin, I think, will give you a possibility to interrupt me. That is why let's make it as interactive as possible. The main idea during the presentation, I would like to show you the basics and also what kind of information we could get from actually X-ray absorption spectroscopy, which you could make at Synchrotron. So let's start. Let's start from the basics. When we speak about X-ray absorption spectroscopy, it means that we need to remind ourselves what does it mean absorption. And for example, if you have some kind of a source of light and you have a detector, in which in this case of this photo will be our eyes, and you have such kind of an object between the source of the light and your eye. Here this is sunglasses. Part of the radiation could be absorbed. And using simple Lambert-Beer law, we could investigate what is the absorption coefficient of this material which we put before the source and the detector. And when we speak about absorption, it is also, we speak about radiation. And in our everyday life, in most of the cases, we speak about radiation in the terms of wavelengths, or some of us use frequencies. I think Laser Lab mostly work with frequencies. When we speak about radiation in the term of synchrotrons, we usually use such kind of a parameter of the energy of photons. But as you could see here, it is quite easily to calculate and to convert the wavelengths to energy and the frequency to energy. And when we speak about synchrotron radiation, one of its unique properties, it is that it covers a wide range of different energies of photons, or a wide range of wavelengths which could be produced by such kind of facilities. Also, this synchrotron light or synchrotron radiation, it has exceptional high intensity in comparison to conventional laboratory equipment. It is thousands times more brighter than a conventional, for example, here, X-ray tube. Also, synchrotron radiation has a it is very nicely collimated, and it has a high coherence, and it helps us to actually to make these measurements of different spectra. In my presentation, I will speak mainly about X-ray absorption spectroscopy, but also when we speak about tomography, when we speak about diffraction, all of these parameters give us a possibility to measure very fast, to measure to have a very nice resolution and to have very nice resolution in comparison to what we can make at our laboratories. When we speak about absorption of X-rays, we speak about photoionization of the electron from the core levels. And the energy of this photoelectron, which actually we excite from core level, for example, K level, LL level, or M level, firstly, we excite it to the unoccupied states, and then we could excite this photoelectron even to the continuum. And the energy of this photoelectron in the continuum will be as a difference between the energy of the radiation, which we radiate our atom in this case, and the binding energy between the electron on this core level, and the nuclei. And let's discuss what actually we analyze during our measurements when we provide X-ray absorption spectroscopy measurements. We actually analyze how the absorption coefficient changes depend on the energy of the photons which we radiate our sample. And for example, let's have here a function of this absorption coefficient, and we change the energy of photons which we irradiate our sample. At first, with the increasing of the energy of photons, the absorption coefficient will decrease, taking into account the probability of interaction of these photons with the atom will be lower. But at some point, when the energy of the photons of the radiation is enough to excite the electron from the M core level will be enough, we will see a drastic increasing of the absorption coefficient. And then the absorption coefficient start to decrease again till the moment when the energy of photons will be enough in order to excite the electron from L core level. And the same situation will appear when the energy of the electron, when the energy of the photons will be enough to excite the electron from the K quotient level to the unoccupied states, or for example to the continuum. And depend on what kind of an energies we use and in what kind of an range we provide these measurements, we will speak about K absorption H, L absorption H, or M absorption H. And during my presentation, you will hear, okay, this spectrum we measured at K absorption H of vanadium, for example, and it means that we actually excite this electron for K absorption shell of vanadium, and see what is going on with this excited electron. Okay, what is also very important when we speak about X-ray absorption spectroscopy, each of the atom has absorption coefficient at a very defined energy range of the photons which we radiate our material. Here, for example, you could see a set of different absorption edges of 3D metals, and you could see that they are separated in the energies. And it means that when we have a very complicated material which contains of different elements, we could precisely focus on one element, and taking into account in the slides further we will discuss it, that from this spectra we could get information about atomic environment. And it means that taking into account that all of these absorption edges of elements are separated from each other, we could investigate the atomic environment of each type of atom individually, even if the material contains a quite large amount of different atoms. And also, when we look more precisely to the absorption edges in the range from minus 200, when I say minus 200, it means that before absorption edges, and when I say let's say 1000 electron volt above absorption edges, I use, let's say, the sign plus. Yeah, and here you could see that before the absorption edge, which is absorption edge, as you remember, it is called the drastic increase of absorption coefficient. We have some kind of interesting features, and also after the absorption edge, we also have some kind of features in the spectra which we measure. And the most intensive position on the absorption spectra which we measure, it is called white line. That is why I also will use it in my presentation. And when we look to the, for example, this spectrum, we could see that we could divide it in two areas. One area, it is called X-ray Absorption Near Edge Structure, and the other one, it is extended X-ray Absorption Fine Structure. And these ranges of the spectrum started from minus 50 before the absorption edge and plus 50 electron volt above the absorption edge, and EXAFS range started above 30-50 electron volt up to 1000 electron volt in our spectrum. Okay, and what kind of information we could get if we investigate this kind of ranges of our spectrum? When we investigate XANES, we could get information about the formal oxidation state of our the absorbing atom in our material, the geometric arrangement, it means how the neighboring atoms arranged around our absorbing atom, and also we could investigate the electronic structure, or for example, what is the unfilled orbitals, or population of electrons in our absorbing atom. When we speak about the range of EXAFS range, we could get information about the nearest neighbors. It is mean what kind of atoms we have around our absorbing atom. Also, we could get information how much of such kind of neighbors we have around our absorbing atom. We could investigate what is the distance between our absorbing atom and the neighboring atoms. And also we could investigate the disorder which we have in our material. In order to understand how we could got the information, let's go to the basics. It is understandable when we investigate XANES region, and in this XANES region we excite our photoelectron to unoccupied states. It means that we investigate what is the structure of the states in our material. That is why how we could get information from about the electronic structure. But when we excite our photoelectron to the continuum, here a quite interesting effect appears. Imagine that we have our absorbing atom, and we excited photoelectron, let's say from the K shell to the continuum. And here we could say about this electron, about this photoelectron, as about electron wave. It is going from our absorbing atom, and as we know, in the material we have neighbor atoms. And this electronic wave could be scattered from these neighboring atoms. And that's how the scattered electron wave appears. And this electron wave could, let's say, coming back to our absorbing atom, or it is also can travel somewhere here, scattered from another neighboring atoms, and there we will have, let's say, more complicated trip which this scattered electron wave made before it reaches the absorbing atoms. And as we know, all of the waves could have a constructive and destructive interference. And actually, depending on what kind of a type of interference appears at our absorbing atom, the absorption coefficient will oscillate, and this kind of oscillations which we have here is defined by what kind of interference of the outgoing electron wave and scattered electron wave we have at our absorbing atom. And that is why analysis of such kind of oscillations will allow us to understand actually what kind of atoms we have, what is the distances between them, and so on. And what is quite important, here you have the dependence of mean free path of the photoelectron depending on its energy. And here we could see that in the range of XANES, it is mean here, when the photoelectron has a very low energy, its mean free path is larger. It means that it could have many of such kind of a multi-scattering paths. Yes, this photoelectron could follow this multi-scattering path, and that is why in this XANES region we could investigate this coordination symmetry, for example, for our material. In the case of EXAFS region, the energy of this photoelectron is large, and that is why its mean free path is low. And it means that mostly for the features in the EXAFS region, we have influence from this single scattering passes. And that is why it is easier for us, for EXAFS, investigate such kind of parameters as interatomic distances, coordination number, in comparison to XANES, where we could get information about geometric arrangement, or symmetry. Now we understand the basics. And if you have any questions at the moment, I think this is a, let's say, moment where you can ask them. Katalin, what do you think? or I can proceed.
I think it's better to proceed because people attending this webinar could also pose their questions in the chat as well.
Okay, then let's go
it's up
further.
to you. Yeah.
Okay, then let's go further. I think one of the most important application of X-ray absorption spectroscopy is defining this average of the oxidation state of the elements which we have in our compounds. And for example, here you could see the position of absorption edges for different different oxides of manganese, and you could see that they are separated in energies. Yes, and when we put them on the graph where on the X we will have the oxidation state of manganese atom in this oxide, and here on the Y we will have the position of which we calculated from the half of the H step. Here we could see the straight line, and that's how you could analyze, for example, the average oxidation state of the material which you don't know. That, for example, you define the position of the absorption edge as a half of the H step, and then you put it to this straight line, and you could easily understand what is the oxidation state. Sometimes you will tell me that it is quite hard to make such kind of a line, but you always could use also, for example, compounds with a zero oxidation state. For example, here you could use metal foil. But in this case, be careful. In this case, you will need to use the maximum of the first derivative in order to make this line. For example, when you would like to work with cobalt atoms in your material to investigate this average oxidation state. And for example, okay, we plot such kind of a straight line based on the reference compounds, and we would like to investigate what is the average oxidation state of our unknown compound. For example, some kind of a new catalysis based on lanthan manganese O3. And when we put the position of the edge, which we define as a half of the edge step, to this straight line, we could define the average oxidation state in our new produced material. But also very important thing what we need to do when we make such kind of analysis, all of these references should have the same ligands around our absorbing atoms. Here you could, for example, see that when I'm working with such kind of a compound, I choose oxides. If, for example, it will be some kind of a chlorides, I need to also work with chlorides in order to keep such kind of a good method how to define such kind of average oxidation state. Also, when we speak about XANES region, we could easily investigate what is the local coordination symmetry we have in our materials. For example, here you could see when we have a quite symmetric local symmetry. For example, for vanadium 3 oxide, we could investigate it by looking what kind of intensity of the pre-edge peak. It means that some kind of a feature before our main absorption edge. Here, for example, we could see that for vanadium 3 oxide, the pre-edge is very low, and it helps us to understand that, okay, in this phase, we have a quite low level of distortion. In comparison, for example, to vanadium 5 oxide, where we have a clearly non-centrosymmetric local structure, and in this case, the intensity of the pre-edge is quite high. The same, for example, we could see for two types of phases of chromium. For example, chromium 3 oxide and chromium 6 oxide, where one of them is, let's say, good for our organism, and the second one is toxic. And having such kind of a possibility to distinguish between different phases, also by analysis of XANES, and especially the pre-edge, allows us to investigate, for example, very complicated materials. For example, now it is quite important to clean all of the to clean the waters after some kind of a complicated industry processes, where we can have in water, for example, vanadium 5, which is toxic, and chromium 6 is also toxic, and how, for example, different plants or algae could transform them from one form to another. And absorption spectroscopy could help us in this case. And as you could see, we measure what is vanadium and chromium we have in such kind of live organism during their living in such kind of contaminated waters, and we see that this algae could transform toxic vanadium and toxic chromium to untoxic forms of these elements by just analysis what is the intensity of the pre-H peaks. Also, when we speak about XANES region and we speak of different symmetries, we could see that the white lines, that's the most intensive point on the spectrum, for example, here for LH, it could be split in two lines, and depend on what is the ratio between first and second peak and what is the splitting distance between them. We could investigate what is actually the type of symmetry we have in our material, and also what kind of what is the level of distortion we have in our material. And imagine that you have different types of catalysis. For example, one of them is octahedra and another is tetrahedral, and you would like to investigate what is going on with your catalysis during the chemical reaction. So you measure such kind of a material before, after, or even during the reaction, and then by analysis of the splitting and the ratio of the first and the second peak, you could understand if the changes in your catalysis appears, and if they appears, what kind of changes you have by analysis of changing of this distortion of your material. The other one, for example, allows you to investigate how you can define the percentage of different phases different phases with different oxidations in your materials. For example, here you have an example how we could investigate very precisely how much of this cerium 3 and cerium 4 and praseodymium 3 and praseodymium 4 we have in our compounds, depend of different chemical reactions which appears with them, with what kind of processes going on them. For example, in this case, it was an annealing of this material, and we investigated how the balance between praseodymium 3 and praseodymium 4 changes with different parameters. But it is, for example, quite important when you work with a new type of catalysis, and this cerium oxide and praseodymium oxide are used as a supporter, or for example, praseodymium oxide is actually used here as a material for electrode for solid state batteries. Also, what kind of analysis you could make using the XANES region of your spectra is making linear combination fitting. Imagine that you have a mixed valence compound, and you think that during the reaction with your material, or you would like to understand what is the composition, the ratio of phases you have in your mixed valency compound. In order to do this, you measure a reference samples which composition you know very well. For example, here the different compounds which I bought and measure their spectra. And then, for example, I measure a mixed valence compound, which was actually a mixture of all of these phases. And then I make a linear combination fitting, and it was then easy for me to understand how much of the atoms, for example, here I measured a sulfur. This is a sulfur KH spectrum of mixed valence compound. It allows me to understand how many atoms of sulfur I have in sulfide form, how much of them is in a pure sulfur, and for example, how much of them in the sulfate. And that's how the analysis could be made using the linear combination fitting. For example, if we are coming back from the model type to a real one, imagine that you have a very complicated sample. It's actually here, this is analysis of a air in Krakow during winter and summer. Here you could see the filter which the scientists put in the morning to the roof, on the roof of AGH University, and then how the filter looks like in the evening. And I think that this is a typical urban situation. And the scientists define what kind of main elements they have in this type of dust, which they gathered on these filters. We measured it at sulfur. We measured sulfur KH spectra, and we found that in comparison to summer, where we have mainly contamination coming from sulfates, in winter air we have some kind of compounds which looks like bisulfates. And in order to check if it is like this, we also measured spectra at potassium KH and make this linear combination fitting. And you could see exactly that from year to year, from sample to sample, we actually proved that in the winter air we have not only sulfates, which is actually can come from the flowers, can come from some kind of standard contamination, but it is also we have bisulfates, which is a result of burning of solid fuel, which actually should not appear in Krakow because we have a green policy. And that's how it helps us, this analysis helps us to make the air more clear in Krakow, because we understand what is the source of such kind of a pollution. Also, as I told you, using the XANES range, we could investigate the electronic the density of states for electrons in our material. Here you could see, for example, how the intensity of the white line, you remember that white line is a, let's say, most intensive point of absorption on your spectrum, changes when you have different atoms here, yeah? And that's by analysis of this intensity and the shape of this white line, you could investigate the density of states of the absorber atom in your material. For example, you are preparing a new type of catalysis or some kind of nanoparticles which you will use in medical applications. And depending what kind of density of states you have on different type of nanoparticles, they will work better or worse, for example, during the phototherapy, or for example during your chemical reaction. And for example, here you could see how the density of states for palladium nanoparticles of different shape changes when actually you change their shape. Now let's come back to the EXAFS region of our X-ray absorption spectroscopy of our absorption spectra. As I told you, in this range we mostly speak about single scattering path of the photoelectron. Here you have this photoelectron going from our absorbing atom, scattered and coming back to our absorbing atom. And these features are hidden somewhere here. In order to work with them, we need to somehow to get them from this our main spectrum. In order to do this, we get rid of this background. As we could see here, this absorption step for us now is a background. We get rid of it. It looks like this. Also, we plot this dependence of absorption coefficient without the background, not in the energy scale, but in the wave number scale, which actually this K wave number could be calculated like this, where E0, it is actually the position of our absorption edge. Then, in order to see more precisely what kind of oscillations we have here, we multiply this function to k square, to this number in square or even in cubic. And that's how kind of oscillation functions then we have. And here it is a window which we use in order to make a Fourier transformation of such kind of oscillated function. And using the Fourier transformation of such kind of oscillation function, we could get amplitudes. main amplitudes, and investigation and the position of these main amplitudes, their intensity actually correspond to the interactions. It is mean interaction between our absorbing atom and the neighbors. For example, here this is closest neighbor for vanadium 5 oxide was oxygen, definitely. So it was an interaction between vanadium and oxygen. The next coordination shell, the next interaction which we have in our material, it was vanadium-vanadium. And in order to precisely to understand how the coordination number changes or how the position between our absorbing atom and atoms in the closest neighboring changes, we need to make some kind of a fitting using different type of programs. They're available and free of charge. And that's how analysis will allow us to understand the coordination number and the distances between our absorbing atom and the nearing atom. Here is an example. For example, we have a quite complicated molecule, a complicated compound where we have a copper which is surrounded by such kind of a boron cage. And using such kind of a procedure which I showed you above, and by the fitting, we could understand how much of the neighboring atoms, of boron neighboring atoms, for example, here, you could see interaction copper, boron, copper. Here, this is some kind of a multi-scattering influence, copper, boron, boron, copper. We could investigate how much of such kind of neighboring atoms we have in our material, what is the distance between our absorbing atom and neighboring atoms, and what kind of distortion we have in our material. So in such kind of a way, we could prove that the model which we think about our compound, it is true or it is not true. And that's how, once again, you could see what kind of information we could get from EXAFS measurements. Once again, local atomic geometry, but definitely here you could see what kind of limits we could have. Identification of near neighbors, what kind of atoms we have around, how much of them we have, the distance between our absorbing atom and the atoms in the neighboring, and also what kind of a disorder we have in our material. Where also EXAFS could be used quite efficiently, it is now in a quite popular topic, is a single atom catalysis. For example, if we speak about single atom catalysis, it means that one atom connected to some kind of a surface, and it means that it does not have any neighbors. For example, platinum single atom catalysis in comparison to platinum nanoparticles. When it is nanoparticles, you definitely should to have such kind of interaction between, for example, here that is this platinum oxide interaction and platinum interaction. Or if it is a pure metal, you will have only this platinum interaction. And when we speak about single atom catalysis, we could see only one interaction between platinum atom and the oxygen on the substrate. So that is why it is used to say that using X-ray absorption spectroscopy and mainly EXAFS region, you could prove that your compound, your catalysis which you make, it is not a small clusters or a small nanoparticle, but it is actually single atom catalysis which you are interested in. That's what kind of information we could get from the spectra and some kind of examples I showed you. But how is that actually when you apply for RIANA and you would like to find a proper beamline for you, I would like to give you some kind of insights to the experiment, how it is organized. Before we start, let's go to the insights, actually, what kind of interactions appears with this light, which is partially absorbed by the material. Definitely part of the radiation will be elastically or inelastically scattered by the material. Part of the radiation will be transmitted through it, but the radiation which is absorbed by the material will cause some kind of effects which appear in our material. Firstly, it will excite electrons, and we could measure the current which is coming from our material when it is radiated by the X-rays. And also, these X-rays will excite fluorescence of the material, which we also could measure. And in this case, when we make X-ray absorption spectroscopy measurements, we could use a standard Lambert-Beer law. We investigate the intensity of the X-rays before the sample and the intensity of transmitted radiation, and using it, we could investigate what is the absorption coefficient value. If we measure fluorescence, which is actually excited by the radiation which we radiate our sample, we could also calculate the absorption coefficient, and also we could measure this current, as I told you, which is emitted by the sample under the X-rays. And depending on what kind of material you are investigating, for example, if you have a high concentration of absorbing element in your material, then in most of the cases you need to measure it in transmission mode. When you have a low concentration of absorbing element, for example, some kind of intrusion or some kind of a small additive to your compound, you will use a fluorescence method. And if you are interested not in the bulk structure of your absorbing atom, but you would like to investigate what is going on the surface, you will measure this current, which is excited by the incident X-ray photons. In order to do this, in order to measure how the absorption coefficient changes depend on the energy of photons, definitely we need to use such kind of a device which is called monochromator. It means that it chooses from the big range of big range of energies of photons, which is produced by synchrotron, only exactly photons with the energy which we are interested in at this proper moment. And this device, it is called monochromator. So in most of the cases, it is so-called double crystal monochromator, where we have here a wide beam. It means that the beam which is produced by the synchrotron, starting from infrared up to X-rays, coming from the synchrotron. Here we have a crystal, ideal crystal in most of the cases, for example, silicon 111 crystal, and Bragg's law appears here. And this radiation is, let's say, interfere, and this radiation with the proper wavelength, which is defined by Bragg's law, is chosen, and then the second crystal is used in order to return the beam to the same direction where it was going down, where it was incident radiation. That is why we use double crystal structure. Here you could see how it is working. Step by step, we are changing the Bragg's law. And we choose the exact energy of photons which we will use in our experiment. And here you could see the curves, which allows us to understand how changing the Bragg angle of the incident radiation and what kind of energy of photons will going out of our monochromator. And in principle, in most of the cases, no matter where it is the beamline, absorption spectroscopy beamline at Solaris or at SRF, ALBA, most of the beamlines have the same constructions, that you have a detector which allows you to detect the incident monochromic radiation before your sample, the detector which allows you to detect the radiation after your sample. Also, you have here a fluorescence detector. And also you have an equipment which allows you to measure the current which appears on your sample. Sometimes you also could have a reference sample. It means that you measure your main sample and the reference sample simultaneously in order to be very sure and very precisely what is the position of this absorption edge of your sample which you are measuring. Also, sometimes you also have a X-ray camera which allows you to see on which place of the sample you are hitting, and for example to choose a proper place on your sample. And here, for example, how you could see more complicated beamline look like, and probably if you could see a lot of equipment here, is the construction is something like this: detector which allows you to investigate the intensity of radiation before your sample, detector of the intensity of the radiation after your sample, which is coming, the detector for radiation, which are coming through your reference sample, and here actually this fluorescence detector. And in principle, when we say what kind of a sample we could measure during our experiment, in most of the cases, we say that powders, it is most easy for us to do. We just make a pellets from these samples. We calculate what kind of amount of material you need to use to prepare such kind of pellets, and you're going to the synchrotron, and for example here you could see a photo how many samples people could measure in a few hours. Then for example you could put your powder sample on the powder, and then another example how it looks like. Also you could measure liquid samples, and for example you could also measure quite interesting sample, as it was experiment connected with food industry. It was a piece of meat which I need to measure and to understand what is the compounds of what is the phases of iron I have in this meat. And if we speak about, let's say, powder, if we speak about, I need to say that we could measure material when we speak about solid state material, we could say that we could measure amorphic samples and also crystalline samples in comparison, for example, to diffraction, where you could measure only crystalline samples. Okay, so for example, thin films also could be measured without any problems, and it will be analog of this powder on the tape, which we have here. So it means that most all type of the samples could be measured during the X-ray absorption spectroscopy measurements. Also, what is important, we could measure, we could provide in-situ experiments. It means that what is going on with the material, not only before and after reaction, not only before and after the heating, but what is going on with the material when we actually make some kind of manipulation with the sample. Here, for example, if we provide some kind of a complicated Fischer-Tropsch synthesis, and we have some kind of a catalysis in the capillary, we heat this capillary, the gas is flowing to this capillary, and we investigate how the catalysis is changing during the reaction. Also, we could make different XAS electrochemical measurements in cells with flow of the electrolyte, without flowing of the electrolyte, and also we could, for example, make XAS operando experiments with batteries. For example, here you could see an example how the experiment of Fischer-Tropsch synthesis was organized. It was a gas dosing system which actually dose hydrogen mixture to the capillary with the catalysis, the gas going through the catalysis. Then we have a mass spectrometer or gas chromatography on the out in order to understand what kind of a gas products we have during the reaction, and we investigate what kind of phases appears during their experiments. And in order to give you some kind of a joke, how the experiments at synchrotrons are realized. This is actually experiment which was realized at the beamline for which I am responsible for. And during the organizing of this experiment, we found a leakage of the sample chamber, because we need to make this experiment in vacuum. And we tried different glues, we tried different sealings in order to do it till the moment when we decided, okay, the last try, let's try to seal using the B-wax. And actually, when we do it on the beamline itself, we just sealed this type of feed through using the B-wax. We succeed, and actually, you could see how the nature could help us to provide such kind of a complicated measurements. And analysis of such kind of XANES spectra during, let's say, changing of the temperature, and analysis what kind of a chemical reaction appears on the catalysis allows us to investigate what kind of transformations we have in our catalysis during the reaction. The same, for example, you could investigate what is going on with electrode material in your batteries during charging and discharging. And here you could see the XANES spectra measured at sodium-ion batteries at antimony L3H during charging and discharging process, and it actually allows us to investigate what kind of shrinkage of the material appears and why it is going in such kind of a way. If you are interested, you could follow this publication. I could say that it is quite interesting. And when we speak about X-ray absorption spectroscopy measurements, we also used to make some kind of a complementary technique. For example, during the same measurements, when you are getting XANES spectra, for example, it is shown here, you could have some kind of a probe of from FTIR spectrometer, or for example from a Raman spectrometer, or for example you can make simultaneously XRD on your sample if it is crystalline. And for example, on this example, I'm showing you that what kind of spectra, XAS spectra we could get, and also simultaneously we are measuring Raman spectroscopy, and in such kind of a way we are getting information about electronic structure, about local atomic structure, and also about vibrational structure of our material during different reactions and different in situ experiments. So at this moment, I think this is all from me. I hope that my presentation could convince you that using X-ray absorption spectroscopy and two ranges of the spectrum like XANES and EXAFS help you, let's say, investigate your scientific ground quite intensively. So I'm thank you for your attention and looking forward to your questions.
Thank you, Alexei. It was really interesting to follow your presentation. I have a few questions, but first there's one question in the chat that I will read it. So the question goes like this: are the edges the same if you have different oxidation states of the metals, vanadium or manganese, but instead of oxygen, what if it's chlorine or fluorine in the compound?
This is a very good.
Sorry. I have a similar questions as Ran, because Ran did a chat question. How can you differentiate from XANES from the pre-edges if you have samples with nanoregions, with different oxidation states or local coordination environment of the metal species? So if you have like a variation in your sample.
Let's say I will divide this question in two. Let's probably go to the slide. Yes.
Yes.
Where this spectra are shown. First of all, let's speak about this manganese. Yes. Okay, and when you have, for example, ligand, which is let's say fluorine, yes, which is connected to your manganese, and when, for example, I could not use it in order to plot this line, I need to make the same references where I will have the same ligands with a very close electronegativity, because when we speak about excitation of the electron from the core shell, it is defined by the interaction of the electron on the core shell between this electron and the nuclei, and also electrons on the outer orbitals influence on it. Yes, and for example, imagine if you have a ligand which has a different electronegativity. Yes, it means that for example, it will, as chlorine, it will take these electrons more on it, and that is why these electrons will less influence on the electron on the core level, and that is why this binding energy will be different, and that is why imagine such kind of a example that you are going to a walk with a 10 dogs in your heads, yes, and what is the probability that one of the dogs will run away from you? And this is a situation when you have some kind of a ligand of a low electronegativity, and these outer electrons actually also interfere with the electron on the core level, and that is why this binding energy is lower. But if you're going to walk with the 3 dogs in your hands, it means that you control your dogs better. Yeah, and this is and this is the situation when you have less electrons on the outer shells, and that is why your core electron is more connected to your nuclei.
It's quite clear. You explained it very well. There's another question in the chat from Saha Debasish. He's asking concerning slide 24, how independent the fitting parameters are. Slide 24, yeah.
In principle, it is also coming back to the question from Niku. When you have a compound where you have different phases, yes. In principle, you then make this linear combination fitting, and you could analyze how much of the phase with, let's say, nano phase, amorphous phase you have, and how much of the phase you have. For example, if you have a mixture of chromium 3 and chromium 6. Then you will have a let's say the same situation as here. You will have a lower intensity of the pre-etch, but you will see it because you know that in the chromium 3 you don't have any pre-etch. And then making this linear combination fitting, you could understand how many of the one phase and then another phase you have in your sample. I hope that, Nico, this answer is enough for you. And now answering the question from the Bashish, this analysis will work good if you have not more than 5 phases simultaneously. This is important. And in principle, you could not just, let's say, make the analysis like this, that you have some kind of unknown mixed valence compound. You choose, let's say, 25 spectra which do not connect with each other, and then you make this type of analysis. Definitely, when you're coming to the synchrotron, in most of the cases, you already know what you have in your sample. At least you use all of the laboratory equipment which you can to use in order to give us some kind of insights in your sample. And then
makes sense because it's energy consuming and also time consuming, and also at the human level, it needs several people to work with it. So yeah, indeed, people should come with some basic knowledge about their samples when they ask for XANES or other related. Right.
The same, for example, here. Yeah, you could have in air almost everything what you can imagine, because in urban air you have different let's say procedures in the plants and so on and so on. So before the researchers came to us, they investigate XRF and understand what kind of elements do they have. Then they also understand what is the position of the, let's say, this filter was during the measurement and who could influence on it. Then also some kind of FTIR spectroscopy was made. So and based on this data, they came to me and we started to think, aha, what it could be? It could be bisulfates. Then let's try to make bisulfates. Let's also make a cross checking if other elements will show something like this. So it's not like, you know, plug and play. You need to make some kind of investigation. This is a quite interesting research work when you work with such kind of a complicated compounds, as for example, Niku asked me.
Okay, thank you. You actually went a bit more than needed with the explanation, but still, I also have one question, if I may. It's related to the extent. To what extent can pre-edged intensity and shape be quantitatively correlated with site symmetry, for example, in centrosymmetric versus non-centrosymmetric environments? And how reliable is this across different elements?
In principle, if we speak about such kind of the more distorted structure you have, the more intense you will have the pre-edge peak. Why it is happening like this? When we speak about photoelectron, yes, and when we speak about excitation to the unoccupied states, definitely this excitation defined. Where I have it? This excitation defined on the golden rule. Yes, what kind of transitions are allowed or what kind of transitions are not allowed. And in the case, for example, of 3D metals, for example, as it is vanadium or chromium, the transition from 1s level here to 3D level is not allowed. But when you have a distortion in your material, you have a hybridization between 3D and 4P levels. And in this case, let's say, transition start to be more probable. And the more this hybridization appears, it means that the more probable transition it is. And for example, if we speak here about this, let's say here, vanadium KH, this is actually a transition to the 3D 4P hybridized orbital level, sorry. And then
my question was actually related exactly to vanadium, but you understood it perfectly. Thank you.
That is why the more distorted structure is, the larger hybridization will be, and that is why the larger pre-edge peak will be. This is actually could be seen here on the example of vanadium. Yes, as you could see here, vanadium 5 oxide is a very distorted structure. Actually, it is square pyramidal. For vanadium 4 oxide, it is a distorted octahedral, and here you could see some kind of less intense. And for vanadium 3 oxide, it is close to the centrosymmetric, and that is why here you mostly have the transition between 1s and 3d, because we know that this transition 1s 3d, it is dipoly forbidden, but quadrupoly allowed, and that is why some kind of probability still exists that you will have this transition. Right. And in principle, yes, you could follow what is going on with the intensity. Again, you could not take the intensity of this pre-edge peak for, let's say, one unrelated compound and try to make a theory of a compound which you, let's say, don't know just by analysis of the pre-edge peak. You need to know about your material something, you need to make some kind of a hypothesis, and then based on it you could make the analysis.
This is interesting for me, at least. The discussion about vanadium, especially vanadium 4+, which is basically what we call VO2 more commonly, because these materials, these compounds behave as phase change materials, reversible phase change materials at specific temperatures. So we need to understand how the transition goes from one shape to another, how the symmetry changes and everything. In any case, thank you for explaining. Thank you for your presentation. If there's anyone wanting to ask any other question, please raise your hand or ask it quick in the chat. In the meantime, let me thank you again for this presentation. Thank you all for attending the meeting. And this, as this presentation was recorded, it will be soon posted online on the YouTube account of RIANA. And okay, there are no more questions. See you next time. Nicu, if you would like to add something, or Alexei, if you would like to.
Just, it was a pleasure. Alexei, it was a very nice talk. So thank you for this, and see you next time, guys.
Thank you very much. Thank you. If you have any questions, you have my email. That is why you could directly contact me. Thank you very much. Thank you.
Thank you.
Bye-bye.
Bye. Bye.